empirical correlations for free convection heat transfer. So, if you're a first-year chemical engineering student, these are the essential equations you're going to need. Think of them as formulas based on actual observation, not just pure theory. They let you calculate heat loss from an object using key dimensionless numbers like the Nusselt, Grashof, and Prandtl numbers. Okay, so there are really three critical things you absolutely have to get right. First, the geometry of your object completely dictates which formula you use. I mean, we have different correlations for a horizontal cylinder than we do for a horizontal plate. And it gets even more specific. For a plate, the equation literally changes depending on whether the heated surface is facing up or down. Second, the very first thing you need to calculate is the Grashof-Prandtl number product. Why? Because its size tells you what kind of flow regime you're in. This is so important because that, in turn, tells you which constants you need to pull from your reference tables to actually use in the main equation. And finally, all of those fluid properties you need, I'm talking about thermal conductivity, kinematic viscosity, all that stuff, they must be evaluated at what we call the film temperature. And that's just the simple average of the object's surface temperature and the temperature of the fluid around it. Let's dive into more detail.
If you've ever looked at this shimmering air over hot pavement and wondered what's really going on, you're in the right place. Today, we're going to break down a core concept in heat transfer that every chemical engineer needs to get a handle on: natural convection. So let's just dive right in with a real-world problem. Okay, here's the setup, a classic problem right out of the textbook. Imagine you've got this really hot pipe just sitting in a cool room. There are no fans blowing, no pumps moving the air, nothing. So how much heat is just pouring off of it? By the end of this explainer, you'll know exactly how to figure that out. But hang on, before we can start crunching the numbers, we really need to understand the physics behind it all. I mean, to figure out how much heat is lost, we first have to get a solid grasp on the why and how of that air moving around the pipe in the first place. So what is natural convection, really? At its heart, it's actually beautiful in its simplicity. It's just fluid motion. In our case, the fluid is air, that gets started all by itself. The engine that drives all this movement isn't a motor or a fan. It's just the fundamental properties of the air, all set in motion by a change in temperature. You've seen this a million times, I guarantee it. You know that wavy, blurry air you see over a hot road in the summer? That's it. That's natural convection right there in action. The pavement gets hot, it heats up the layer of air right about it. That air expands, which makes it less dense than all the cooler air surrounding it. And what does a less dense fluid do inside a denser one? It rises. And as it rises, it carries all that heat energy with it. That movement is convection. Now, it's one thing to see that shimmering air and know what it is, but it's a whole other thing to actually quantify it, to put a number on it. And for that, engineers have this incredibly powerful toolkit filled with something called dimensionless numbers. These are like secret codes that help us describe really complex systems, and what's amazing is they let us scale our understanding. The same rules that apply to our 1-foot pipe can also apply to, say, a massive industrial reactor. And the star of our show today is this guy, the Grashof-Prandtl product, or GPR for short. This one number tells us a whole story. You can think of it as a battle, a tug-of-war between two different forces. On one side, you have the buoyancy force. That's the force trying to lift the hot air up and away. And on the other side, you have the viscous force, which is basically the air's own internal friction or stickiness that's resisting that movement. The final value of this GPR number tells us who wins that battle, and, most importantly, which equation we need to use to solve our problem. Okay, I know this formula can look a little scary at first, so let's just break it down piece by piece. Think of it like a fraction. Everything on top represents the forces that are creating the flow, and everything on the bottom represents the forces that are resisting it. So, up in the numerator, our driving forces, we start with G, gravity, right? Makes sense. Without gravity, there's no up, so there's no buoyancy. Then there's beta, the thermal expansion coefficient. That just tells us how much the air puffs up and gets less dense when you heat it. Bigger beta, stronger lift. Then we have the temperature difference, the wall versus the air. This is the real engine of the whole process. A bigger temperature difference creates a way stronger convection current. And then, notice this, the pipe's diameter is cubed. That's huge. It means that making the pipe just a little bit bigger has a massive effect on the flow. Now for the bottom part, the resisting forces, we have nu squared. That's kinematic viscosity. Just think of it as the air's stickiness, trying to hold everything in place. So this one number packs all that physics together and tells us who's winning the tug of war. All right, enough theory. It's time to roll up our sleeves and actually solve this thing. We're going to go through it together, step by step. So here's our game plan. 5 simple steps. First, we'll find something called the film temperature. Then we'll use that temperature to look up all the air properties we need. After that, we calculate our big Grashof-Prandtl product, use that to find another number called the Nusselt number, and finally, we solve for the heat transfer coefficient, which we call H. First up, the film temperature. So you might be wondering, why do we even need this? Well, the properties of air, like its viscosity and how well it conducts heat, they all change with temperature. So we need to figure out those properties at a temperature that's representative of that thin film of air right next to the pipe. The easiest way to do that is to just take the average of the pipe's wall temperature and the temperature of the air far away. And a quick calculation gets us 132.5 degrees Celsius. Now, this is really important. We have to convert this to Kelvin, so 405.5 K. We have to do this because a lot of our property calculations, especially for that thermal expansion coefficient, rely on an absolute temperature scale. Okay, now that we have our film temperature, we can do what engineers do all the time. We go to the appendix in a textbook, or more likely these days, a digital database, to find the physical properties of air at precisely 405.5 Kelvin. And here they are. We've got K, the thermal conductivity, beta, our expansion coefficient, nu, the kinematic viscosity, and the Prandtl number, PR. Okay, great. We now have all the ingredients we need for that big Grashof-Prandtl formula. And this is the moment we've been building up to. We take all those properties we just looked up, plus gravity and our pipe's diameter, which is 0.3048 meters, that's our characteristic length, and we plug every single one of them into that Grashof-Prandtl equation. And what pops out? We get a Grashof-Prandtl product of 1.571 times 10 to the 8th. Whoa, that is a big number. And it's not just a random string of digits, it's telling us something really important. For our pipe, the buoyancy forces are absolutely crushing the viscous forces. This means we have a very strong, well-developed natural convection flow. So, what do we do with this giant number? Well, we use it to pick the right recipe out of our engineering cookbook. See, we often use what are called empirical correlations. These are basically formulas that other people figured out from doing tons of experiments. For a Grashof-Prandtl number in our range, the textbook gives us a nice, simple formula. The Nusselt number equals C times GP to the power of M. And based on our value, the constants we need are 0.53 for C and 1/4 for M. So we plug in our numbers, and we get a Nusselt number of 59.4. Now, this is a fantastic result because it tells us something profound. It's telling us that the heat transfer from our pipe is almost 60 times greater than it would be if the air was just sitting perfectly still and heat was only moving through by pure conduction. That right there is the power of convection. We are on the home stretch now. The Nusselt number is really just a bridge to our final goal, which is H, the heat transfer coefficient. We just have to rearrange the definition of the Nusselt number to solve for H. So it's simply the thermal conductivity K times the Nusselt number we just found, all divided by the pipe's diameter D. And that gives us our heat transfer coefficient, 6.63 watts per meter squared degrees Celsius. This number is incredibly useful. So what does it mean? It means that for every single square meter of the pipe's surface, and for every single degree of temperature difference between the pipe and the air, 6.63 joules of energy are being carried away every single second. So we have our H value, we have all the pieces of the puzzle. Now we can finally go all the way back and answer that original question we started with. And here it is, the final answer. Using the simple formula that heat flow equals H times area times the temperature difference, we find that our hot pipe is losing 1.49 kilowatts of heat for every single meter of its length. To put that in perspective, that's like having a powerful space heater running, and all that energy is just coming from the heat pouring off the pipe into the air. Now, this brings up a really important reality about engineering. The simple formula we used, it was fast, it was effective, and it gave us a Nusselt number of 59.4. But the source material also gives a much more complex but more accurate formula called the Churchill-Chew correlation. If we use that one, we'd get a result that's about 8% higher. And this is a perfect example of the kind of trade-off engineers make every single day. Do you need a quick, pretty good answer right now, or do you need to spend more time to get a more precise one? So there you have it. We walked through the entire process for a horizontal pipe, from the basic physics all the way to a final number. But what this journey really shows is a method, a way of thinking about these problems. The specific formulas might change if you have a vertical plate or a sphere, But those core principles, using dimensionless numbers like Grashof and Prandtl, and identifying a characteristic length, they stay the same. They give you the power to tackle almost any geometry. So the real question for you is, how would you start to adapt this process for a totally different shape? That's the next step on your engineering journey.